So we have in last lecture we have concluded the discussion of fermions, and now we go to the last missing piece before we can talk about the QED. Is how to quantize a Maxwell field. Okay, how to get photon. Okay, and so today we start with okay. So this is a short chapter. I think we should be able to finish it just this week in 2 lectures. So first, let me just remind you some aspect of the classical Maxwell theory. And then we will talk about this quantization. Okay. So so the Lagrangian, say for the classical Maxwell theory, can be written as Lagrangian density, can be written as F mu mu. So F mu mu is just the standard partial mu a nu equal to partial nu a mu, and the J mu is just electromagnetic current. Okay, J mu is just magnetic current. Okay, and then so from this Lagrangian density, then you can derive the equation motion, which is just the Maxwell equation. Okay, so the Maxwell equation is given by partial mu F mu nu equal to minus J mu. Okay, and so this is the familiar equation which we see from classical electrodynamics. Okay, and so and if you act partial mu on both sides, so now let's consider act partial mu on both sides. Since F mu mu is by definition symmetric, it's anti-symmetric, so this is automatically 0. And so this tells you that the current, by consistency, the current has to be conserved. Okay, the current which are appearing at the right-hand side of the Maxwell equation have to be conserved. Otherwise, you don't have a consistent equations. Okay. And so another important feature of the Maxwell equation is so-called the gauge symmetry. So the Maxwell action, both the action and the equation motion are invariant under, say the L, the action. So you integrate this over full space-time. So it's invariant under the following transformation, that A mu goes to A mu prime equal to A mu plus partial mu lambda x. Okay, and here the lambda x is an arbitrary function of space-time coordinates. Okay, it's an arbitrary function. So the fact that the Einstein or the fact that the Maxwell theory the action is invariant under this transformation is that you can easily check yourself under this transformation. F mu mu does not change. Okay, so the transformation between this and this, they just cancel each other. And so F mu mu does not change, And then you see the equation motion, of course, is invariant under this transformation because F mu does not change and J mu does not transform. And also the action is invariant because the F mu does not change. And naively, this term does change under the transformation because you have this partial mu lambda. But the additional term corresponding to partial mu lambda times J mu. But then you can do integration by part under the integration, and because J mu is conserved, and so the action is invariant. Okay, so the action is invariant. And so this symmetry is a little bit different from the symmetry we have discussed before, because the symmetry depends on arbitrary, depend on the function of arbitrary space-time. Okay, of space-time coordinates. Okay, so for this reason, and the previous symmetry we have talked about, the transformation parameters are independent of the space-time coordinates. Okay, they're constants, and so that's why this is called the local symmetry. Sometimes also called, just for historical reason, it's called the gauge symmetry. Okay, it's called the local symmetry or gauge symmetry. And yeah, in contrast to the global symmetry which we encountered before, whose transformation parameters are space-time independent. Okay. So the gauge transformation, the gauge symmetry and the global symmetries, even though they are all symmetries, but they have very, very different physical interpretation. Okay, so global symmetry is a genuine symmetry. Say when we say the series translation invariant, means that when you what's happening here in Boston is the same happening in, say, in Washington D.C. Okay, it's genuine, things are invariant under that. But the local symmetry is very different. Okay, so the local symmetry means so the presence of a gauge symmetry implies that the system has redundant degrees freedom. Okay. So let me just give you a cartoon to illustrate this point. So the space of A mu, of course, is it's an infinite dimensional space. But let me just imagine this blackboard is the space of A mu. Okay, this plane is the space of A mu. And this gauge transformation can be viewed as the following. Say for each A mu, imagine you make a gauge, make an arbitrary transformation, this lambda x, and so this line. So let's denote the space of lambda x. Okay. So at each point A mu, you can make a transformation for different lambda corresponding to different points. Okay. And if you start with a different A mu, then you have a different yeah. So each of them is called so each of them is called the orbit of gauge transformations. Okay. And they are parameterized by lambda. Okay, and they are parameterized by lambda. And the fact that the physics is invariant under this transformation means that the physics at this point for this choice of A is the same as for this choice of A. Okay, and similarly, the physics on this choice, just physics on the same orbit is the same. Okay, they describe the same physics. So in other words, only a cross section. So you can have many orbits. Okay, so in each orbit we can just choose a representative point, and then the physics only depend on a cross section of these all these different orbits. Okay, so physics only depend on a cross section. Okay, so a section, a cross section of this orbit. Okay, yes. Yeah, lambda. So different point corresponding to different lambda. So you view this as really as an infinite dimensional space, and so each point corresponding to a different choice of lambda, because lambda can be an arbitrary function. Okay, and yeah. So yeah, let me just parameterize by lambda x. Okay. So this means, so the fact that we can choose this lambda arbitrarily, so this means there's, so in this case, so there's one scalar degree of freedom. So lambda is just a scalar field, can be viewed as a scalar field in space-time coordinate. So there's one scalar degree of freedom as parameterized by lambda. Is redundant. Okay, because any point on this orbit, they carry exactly the same physics. They carry exactly the same physics. And so any questions on this? Okay. So if you remember, in classic ENM, when you solve the Maxwell equation, we have to, the physics, the physical object or the physical quantities, they're all independent of the choice. Yeah, so each choice of this section is called a gauge. Okay, choice of a gauge. And so the choice of a section is called the choice of a gauge. So when you solve the Maxwell equation, typically you choose such a section, you choose a gauge, and then you can just solve the Maxwell equation within that gauge so that you no longer have redundant degrees of freedom. Okay. So often this gauge is chosen so that you can solve the Maxwell equation, simplify the task of solving the Einstein equation, the Maxwell equation. Okay. So we often solve Maxwell equation by fixing a gauge. Okay, so let me. So there are two common examples which we use to solve the Maxwell equations. So one is called the Coulomb gauge. Okay, so in this gauge, you require the spatial component of A mu satisfy this equation. Okay, so I will use the notation that a mu equal to phi. So the zeroth component I call phi, and then the spatial component, the time component I call phi, the spatial component I just call a vector. And also I often write J mu as the rho, which is a charge density, and then the electric current J. Okay. So in this Coulomb gauge, then the Maxwell equation simplify. Okay, so you look at this equation and you look at different components. Okay. And so we're not going to detail. Let me just write down the answer. When you impose this Coulomb gauge, you find that the Maxwell equation become the following. So let me call this equation 1. Call this equation star. So you find that in the Coulomb gauge, you find that the equation star become. So the time component become so-called the Poisson equation. And then the spatial component become like this. Okay. So you get these two equations. So let's just remind you a little bit of the physics encoded in this two equation. Okay. So this is the equation which we can use rho, the charge density distribution, to solve for the electric potential. Okay, for the scalar potential. But notice that this equation does not involve in time derivatives. Okay. So this is not dynamical. So phi is not dynamical. It's determined by rho instantly. Okay, so this means that the configuration of phi at a given time is just determined by the configuration of rho exactly at that given time. Okay, and there's no dynamics in the phi itself. Okay, there's no time derivative in phi. There's no dynamics in the phi itself. So this is first. The second thing is that let's see what this Coulomb gauge condition means. So if you look at this condition, when you go to momentum space, say let's Fourier transform, go to momentum space, and then that just become k dot a equal to 0. Okay? So that just means that yes?
Technicality, but in the expression for a and shouldn't it be minus phi? Because it's like a sub mu, right?
Which should be minus phi.
Like a sub mu equals minus phi comma a. Because like in the
sorry, which equation you say is
yeah, right under Coulomb gauge. Like in there.
You mean here?
Yeah, above that, yeah.
No, this is my convention, right?
Oh.
Yeah, this is my convention. Yeah, you can call it minus phi, you can call it positive phi. Yeah. So in momentum space, you can just write it as this. So this just means that the component of A parallel to the momentum is 0. Okay, A only have component which is perpendicular to the momentum. Okay, to the spatial momentum. So if I we can write A as the longitudinal plus A transverse. Okay, so longitudinal is defined to be the component of A which is proportional to K. So AIL, when you go to the Fourier space, will be proportional to K. Okay, and then AIT will be transverse to K, means that AIT dot Ki equal to 0. Then the Coulomb gauge means this means that A is equal to A transpose. Okay, just A transpose. Just longitudinal part is 0. Okay, the part proportional to the momentum is 0. So now we can already see what. So just combine these two features. Then how many dynamical degree of freedom does the Maxwell theory have? Yes?
2.
Why is 2?
Yeah, because phi is not dynamical, so you don't care about that.
Yeah.
You have 2 transverse.
That's right. So phi is not dynamical, we don't care. And then this AI is 0. And so you only have the transverse component. Transverse component is perpendicular to the momentum direction, and you only have 2 independent components. Okay. So we find there are only 2 transverse dynamical degree of freedom. And indeed, this is the 2 polarizations. Classically, this just corresponding 2 polarizations of electromagnetic wave. Okay, so if you look at the EMF, so you only have 2 independent polarizations. Okay, you only have 2 independent polarizations. So this is the story for the Coulomb gauge. So Coulomb gauge is very convenient and has been is widely used, in particular in the non-relativistic situations when you don't involve very fast velocity. But the Coulomb gauge, of course, is not perfect. So there's some drawbacks of the Coulomb gauge. So first, there's no manifest Lorenz symmetry. So the Maxwell equation is manifest Lorenz covariant, and so but the Coulomb gauge is not. Because this condition certainly is not covariant. Okay, it's not covariant. It's not the same in different frame. Okay, and one consequence of this manifest this loss of the manifest Lorenz covariance is this phi equation is determined instantaneously. So we know that when you have the relativistic theory, then everything should propagate smaller than the speed of light. Okay, and so you cannot have such kind of instant action. Okay, at the distance. So this implies instant action at the distance. Okay. And so, and this is an artifact of the Coulomb gauge. Okay, this is an artifact of Coulomb gauge. And the underlying physics is certainly not. Okay, so for example, one consequence of this is that the causality is not manifest. Okay, because you have instant action at the distance. Okay. But remember that phi itself is not physically observable, so we cannot observe phi physically. So it's okay for phi to have instant this action But of course, the electric field and magnetic field, they are causal. Yes? Yeah, we will not. Yeah. Yeah, will be manifest. Yeah. This also will not break the causality. It just the causality is not manifest. Because just phi is not the physical, directly observable. Yeah. Okay, so then that motivates. So that's why the Coulomb gauge are mostly suitable in the case which involving no velocities in the non-relativistic situation, which So the second. But then this still, but in a more relativistic situation, people always consider, often consider so-called Lorentz gauge. So the Lorentz gauge is defined to be partial mu a mu equal to 0. Okay. So the partial mu equal to 0. Now this equation is covariant. Okay, because index are contracted. So this is a covariant equation. Okay, so this is a covariant equation, and so the Lorentz covariance is manifest. Then the Maxwell equation. So under this gauge, then the equation star now become very simple. Okay, just become that. Okay. So you see, this equation is indeed covariant. Okay, so the derivative contracted, and then you have J mu. Okay. So now this is like something we are familiar. This is like you have 4 independent scalar fields, massless scalar fields, but each of them have a source. Okay. So that's the situation which you actually see in your P set. Okay. In P set, you look at the scalar field with a source, and so this is like 4 independent scalar fields. Each is sourced by J mu. But of course, they are not independent because we have this gauge condition. Okay, we have this gauge condition, and also this gauge condition, of course, is compatible with this equation because if you act partial mu, partial nu on both sides. And then because of this gauge condition, this the left hand is 0, and the right hand side is also 0 from the current conservation. Okay, from current conservation. So now let me also make some remarks on the Lorentz gauge. The Lorentz gauge is very convenient because it gives you seemingly decoupled equations between different a mu, okay? Between different a mu. So, but Lorentz gauge also suffers a little bit problem, okay, inconvenience, because the Lorentz gauge does not fix the gauge completely, okay? So after Lorentz gauge is not fix the gauge freedom. Completely. So there's still some residue gauge symmetry left. Okay, so consider a mu goes to a mu plus partial mu phi. Okay, and if phi satisfies partial mu equal to 0. Okay, if phi satisfies this equation, and then this preserves the gauge. Preserves the condition. Preserves this condition if phi satisfies the equation. Okay, so this tells you that the gauge freedom is not completely fixed. Okay, so now let's if you look at this freedom, so here it's like you can shift lambda is an arbitrary scalar field. It's an arbitrary function. So you can view it as an arbitrary scalar field, okay, with no constraints, okay, with no constraints. We can say it's an arbitrary off-shell scalar field, okay. But now after you fix the Lorenz gauge, you find that there's still some remaining gauge freedom, and the remaining gauge freedom corresponding to an on-shell massless scalar field. Okay, there's still, if phi satisfies this, because this equation is like a massless equation of motion for massless scalar field. And so after you fix the Lorenz gauge, there's still a freedom of the on-shell massless scalar field left. Okay. So this is the first remark. So the second remark is related to later we are going to treat how we treat the say this Lorenz gauge to quantize it. Okay. So there's an alternative way. So you can just fix the Lorenz gauge, say in your equation motion. Just in your equation motion anywhere you see this thing, you set it to be 0. Okay. But we can also actually impose the Lorenz gauge at the action level. Okay. So we can fix the Lorenz gauge at the action level. As follows. So we consider a new action, say a new Lagrangian related to the previous one by a shift like this. Okay, and lambda here, let me not use lambda because so that to be not just psi. Okay, so psi here is arbitrary constant. Okay, psi is arbitrary constant. So now let's look at this new theory, which is obtained from the original theory by adding this term. Okay, so now let's look at this equation motion. So if you look at this equation motion, then you find it's given by the following form: partial square a mu. So partial square just means the partial mu. Okay, and then you have lambda minus 1 partial mu a mu equal to j mu. Okay, you find the equation like this. Okay. Sorry. So you see an equation like this. So this is equation. You get this new term because of this new term. Because of this term in the Lagrangian. Okay. So now let's act partial mu on both sides. Since the current is conserved, and then when you act partial mu here, you get partial mu a mu, and then you just combine together, you find you get partial square partial mu a mu equal to 0. So if you act the partial mu on both sides, you find that this equal to 0. So now we can impose partial mu a mu equal to 0. Okay, we can enforce with star star by imposing boundary conditions. So that this equation only has trivial solutions, which means that this partial mu and mu equal to 0. Okay. Sorry, I'm running out of space here. Okay. So you can so you have this equation, and now you can enforce that the Lorenz gauge by putting the boundary conditions, so that this equation only have 0 solution. Okay, and then equivalently, then you have imposed the Lorenz gauge. But the nice thing of this approach is that now you can treat it as action level. And the advantage we will see later, okay? Because in quantum theory, the action is very important, in particular when you do the path integral. In particular when you do the path integral. Any questions on this? Yes?
Can you go into a little more detail about like what the specific boundary condition would be, like make it on it?
Yeah, we will do it later in your PSAT. Right. Yeah. So we will touch on this question when we will touch on this question when we quantize it. This feature will become very important, and then you will have opportunity to work out in detail in your PSAT. Yeah. Other questions? Yes. Yeah, just a little bit easier. Yeah, just a yeah. Later when we do the path integral, you will see it's easier. Yeah. Classically, there's no difference, but quantum mechanically, we always want to do it at the action level. Yeah.
So do we have an extra constant now?
Sorry.
Do we have an extra?
Yeah. Yeah, we have actual a constant, but the physics should not depend on this constant. Other questions? Okay, good. So let me just point out when psi equal to 1, the story is particularly simple. So for general psi, you get this more complicated equation. But for psi equal to 1, you notice that here this term just 0. And then you just, even with this new Lagrangian, you get exactly the same equation motion as in the as if you have imposed the Lorenz gauge in the equation motion. Okay, so psi equal to 1 is particularly simple. So psi equal to 1 is particularly simple for a reason. So if you put psi equal to 1 here, okay, if you put psi equal to 1 here, then you will find that this term actually cancels with some of the term in this L exactly. So you actually when psi equal to 1, you find that the action now become the Lagrangian become the following: become 1/2 partial mu A nu partial mu A nu minus J mu A nu. Okay, just become very simple. Again, just the action now become like you have just a bunch of free scalar fields. Okay, massively scalar fields. Okay. Good. Any questions? Yes? Oh, sorry. Yeah. Yes. So this mu should be downstairs. Right. Okay. So just like even at the action level, it looks like you have 4 decoupled massless scalar fields. Okay, good. So now we are ready. So this is a quick review of the classical story. So now let's discuss how to quantize it. Okay. And so we will first do the standard canonical quantization. Okay, write down the most general solutions to the operator equations, and then we will discuss using the path integral. Okay, using the path integral. The path integral is convenient for treating interactions, and so canonical approach is the convenient for understanding what's the physical degree of freedom, to understand what's going on physically. Okay. So for simplicity, let's just forget about the J mu. Okay. So let's just look at the Maxwell series itself. So J mu does not do anything in terms of quantization of the Maxwell series. Okay. So we don't need to worry about it when we think about when we quantize this series. So this series is quadratic in A mu. So this is what we call the like a free series, okay? Because it's quadratic in A mu. There's no interaction. Okay. So in the absence of source, in the absence of the charge density or current density, the Maxwell series does not have low self-interaction. Okay, have low self-interaction. So the photon is free. Okay, in the absence of the sources. So this is a free series. But the quantization of this series is actually very subtle due to the following reasons. Okay. So subtleties. Quantization. First, you said because of the gauge symmetry, so there's a redundant degree of freedom. Okay, they are redundant degree of freedom which are unphysical. Okay, which are unphysical. So we want to only should quantize only physical degree of freedom. Okay, so this is much more subtle at the quantum level than at the classical level. So at the classical level, we just fix the gauge. Okay, then that's it. And but at the quantum level, things fluctuates. Okay, so you have to make sure the fluctuation you look at corresponding to physical fluctuations, not corresponding to fluctuations of those unphysical degrees of freedom. Okay, and so that makes the quantum theory more subtle compared with classical. Okay. And the second subtlety is that F mu is antisymmetric. So the second one is more technical. So this one is very conceptual. It's antisymmetric. So that means there's no term, partial zero, A0 term, okay? Because this is symmetric between the two indices, and these are antisymmetric between two indices. there's no A0, partial 0 A0, then that means there's no time derivative term for the A0 component in your action. Okay? So that means L does not contain time derivatives of A0. So this means that if we look at the momentum conjugate to A0, which we should look at the derivative of the Lagrangian density divided by time derivative of A0, this is just identically 0. So again, this corresponding to a constrained equation. This is not. This does not express a canonical momentum in terms of the A0 dot, okay, or the time derivative of anything. So this is a constrained equation. And again, if you want to treat properly, we have to use constrained quantization. Okay, we have to use constrained quantization. And so this leads to subtleties. Okay. So because now, remember we said since that the constraints are lowering when we already discussed for the Dirac equation, and there we avoided going into such kind of constrained quantization by using a trick. And here we will do similarly. Okay, we will not directly deal with constrained quantization, but we use some trick to go around this issue. Okay. Good. And so let me just write down by passing the canonical momentum due to AI. Then this is AI dot. Okay, dot is the time derivative, and then you can. So this is corresponding to minus F0I. And then this gives you just EI. Okay, so the canonical momentum corresponding to AI is just electric field. Okay, so it's just electric field. Okay. So with this warning, and then let's proceed to quantize the theory. Okay. So as we said, we want to only quantize on a cross section. Okay, we don't want to quantize those unphysical degrees freedom. Okay, those unphysical degrees freedom. And so we have to fix the gauge. Okay, so we have to fix the gauge. Okay, so first let's do see how to do it in the Coulomb gauge. So Coulomb gauge is conceptually simple. Okay, so in this case, so in the absence of source, let's look at that two equations, and then again we follow the same strategy as before. We follow the same strategy before. We first find the most general classical solution, and then we turn that into the quantum operator solution. Okay, the same strategy. So in the Coulomb gauge, then we have two equations, and then we just have phi squared equal to 0, and now partial mu A mu partial mu AI now equal to phi. Okay, we have these two. So that two equations, because J is equal to 0, and then become that two equations. Okay. And also we have the gauge condition, which means that AI must be transverse. Okay. So here are the equations we have to satisfy. Okay, here are the equations we have to satisfy. So here, in this case, we don't have this problem with the constrained quantization because phi is not a dynamic variable. Okay, so we don't have to worry about quantizing it. Okay, and in fact, if you look at this equation, so this is so-called elliptic equation, and then you can impose the boundary condition. So if you require phi to go to 0 and infinity, okay, spatial infinity, and then this equation only have identical 0 solution. So the phi you can just set it to be 0. So phi is just 0. Okay, and so now since the phi is just 0, we don't have to worry about this canonical. We just don't have to quantize phi. And now the equation for AI become very simple. You just have partial mu AI equal to 0. And now this just become maximally scalar field equation. Okay, this is just like you have a maximally scalar field equation. Okay. So now we can just proceed with the quantization. Okay, but remember AI is only transverse. Okay. AI has to be transverse. Okay, so now we impose this as an operator equation. So all this should be interpreted as an operator equation. Okay, when we quantize it, and so that means that AI as an operator can only have a transverse component. So now we can just quantize the theory. Okay, so the solution to this, of course, we already know. Okay, so we can just now proceed with the quantization. So the first step is that we have to write down the canonical commutation relation. So this means that AI with pi I, pi j should be I delta ij. Okay, we have to impose this. Okay. So this equation in the current context, if I write it carefully, is the AI t xi tx, and then ej tx prime. So this should be equal to I delta ij delta x minus x prime. Okay. Yes.
So when we have to choose like the Pixar gauge to start quantizing the theory, is there a reason why we're using the Coulomb gauge here? We kind of discussed it violates causality and stuff like that.
No, it does not violate causality, right? Just causality is not manifest. It does not violate causality.
What does that mean? To be not manifest?
Means that the so manifest is that at every step you see the causality is preserved, and not manifest that you have to check it to make sure causality is preserved. Yeah. So I say this equation is covariant. I don't have to check it. I know this is covariant. I look at the equation, it's covariant. Okay. But then if I look at this theory, I don't know that theory is covariant. But this theory is actually covariant. So the way to check its covariant is you check its observable quantities. Yeah, but phi is not observable quantity. So that's why we say it's not manifestly causal. Yeah. So Coulomb gauge is a convenient gauge to use. Yeah, even quantum mechanically. Yeah. Yes.
So the canonical momentum here is not related to like the field momentum E cross B, right? Not related. Like we have the momentum carried by the field E cross B.
No, have nothing to do with that. No, this is the canonical momentum conjugated to the field. And that momentum you're talking about is the momentum carried by the electromagnetic field. It's the space-time momentum carried by the electromagnetic momentum, by the electromagnetic field. So that's analog of the Noether charge. That momentum is the analog of the Noether charge. Yeah, for the scalar case. Yeah. Remember, in the scalar case, there are also two momentum. Yeah. Other questions? Okay, good. So, but this is wrong, okay? So if you just naively write down this canonical commutation relation, this is wrong because this equation is incompatible with the Lorentz gauge condition, okay? So imagine you just add the derivative on this, do the derivative on x, and then since it's the this is the operator equation, and then so if I just so let me call this equation 1. So if you act partial I on 1, then the left hand side I have A T x and EJ T x prime. On the right hand side, then I have the delta function. And let me just partial I delta. Okay. And the right hand side is non-zero. It's just a derivative of the delta function. But the left hand side, according to this, should be 0. Okay, so we have a contradiction. Okay, so this equation cannot be right, and the reason is simple. It's because this equation also includes the longitudinal discrete freedom. But we said AI can only be transverse. Okay, but this equation actually is a 3-component. So also include this the longitudinal. So we should not include that. Okay. So what we should do? It should be only look at the AIT. Okay. So in fact, we should look at AIT Tx, and with its conjugate momentum, which let's call it pi j T Tx prime. So this should be I delta Aj. That's 3 x minus x prime. Okay, so we should look at the only the transverse component. Okay, and the pi I, the transfer the conjugate momentum for the transpose AI. If you start from here, okay, so you easily convince yourself from here. You can find it from yourself. Okay, and this is just equal to partial 0 AIT. Okay, it's just partial 0 AIT. Just the time derivative. So remember here, EI is equal to partial 0 AI minus partial I A0. And this part is 0 because phi is equal to 0. And then here, if you take AI to be transposed, and then pi transpose just equal to that. Okay. But this equation is still not correct because the left-hand side is transverse, but the right-hand side is not transverse. Okay. So here we have to impose a transverse projector. So rather than write it as a delta Ij, what I should do is I write it as a transverse projector. Okay. So Pij is that when you act, so AIT. So Pij is the if you act this on Aj, it projects into the AIT. Okay. So this is the transverse projector. And then now this is a consistent equation. Okay, now this is a consistent equation. Okay. So this transverse projector you can easily write down in momentum space, but in coordinate space it's a little bit awkward to write it down. So formally in coordinate space, this Pijt can be written as following: as delta Ij minus partial I partial J divided by delta square. Okay, and so so you can easily understand the meaning of this equation, because when you act on the anyway you can check yourself this works. Okay, and to understand what this you can check formally yourself. This works. Okay, give you to the transpose. You can understand this equation by going to momentum space. Going to momentum space, this just become Ki, this Kj, this just become K square. Okay, this just Ki times Kj divided by K square. Okay, and so the coordinate space definition of this just corresponding to the Fourier transform of the momentum space expression. Okay, just formally write it as this. Okay, it's formally write it as this. Good. Any questions on this? Yes. Yeah. It's the we just use this to denote use notation to denote what we mean by the Fourier transform of the momentum space expression. Yeah. Yes.
Do you mean like the inverse of the Laplacian when you write like 1 over grad squared?
Huh?
Do you mean like the inverse of the Laplacian when you write like something over grad squared?
Yeah, I just this is just formal notation to make one thing you can check. You say if you have something like this, partial I, Aj, partial, so this is a longitudinal part of A. So one thing you can check yourself is that if you act this on the partial J AI, and then this will cancel with the downstairs, and then that gives you the transverse part. Anyway, just try to treat this as a rotation. Okay. So momentum space is very easy to understand. Okay, so this is now our canonical commutation relation. And now we only quantize the physical degree of freedom. Okay, we only quantize the transverse degree of freedom. And everything else we don't worry about it. Okay, everything else we don't worry about it. And the transverse part just satisfies the standard massless equation motion. Okay, so remember the transverse part just satisfies the standard equation motion. So now we can just immediately write down the most general expansion of AIT. We just write down the most general theory satisfies this. This is just like a massless equation. So we can just write also what we do previously. Okay, and then we can just write down, say A. So previously we just say AK, IKX plus AK dagger x minus IKX, and then omega K in this case would be just equal to K. Okay, because for massless. But now here we have two independent components. Okay, so we have two independent components. So essentially we have two actually independent solutions. Okay, so now let me parameterize the two independent solutions by a polarization vector, to write more generally by a polarization vector like this. r equal to 1 to 2, epsilon I r. Okay, and then this is r. This is r. Okay, so epsilon r one and 2 are a basis of transverse vectors. Okay, because AI have to be transverse. Okay, so so essentially you can treat it as polarization. Okay, associated with this AK. Okay. So by definition, this should satisfy, say, I R Ki equal to 0. So this should be transverse. Okay, so we also define them to be orthogonal to each other. So R and S here just 1, 2. Okay. So this is orthogonality normal to each other. Orthogonal. Okay. And so they also satisfy the condition. So if you have two independent vectors, then when you sum them together, and then you should get the projection operator. Okay, so you should get the Pij Tk. Okay. So epsilon I, they should be they are k dependent. They depend on the spatial momentum because they have to be orthogonal to the momentum. Okay, and this is just a momentum space version of this. This is the delta Ij. Okay. So this is orthogonal condition. This is a completeness condition. Okay. It's a completeness condition. Any questions on this? So now this is the expansion for AI. Okay. So the only difference from the scalar case is that now here you have two independent vectors, and now we have allowed the general polarization. Okay, associated with I have parameterized the general solution using two independent polarization vectors. Okay. So now you can now plug this back into here. Now you can find the commutation relation between A and A dagger. Then you find, as you would expect, that they satisfy the standard. So from the commutation relation, you find that the AK R and AK prime S dagger is equal to delta S okay. Means the rest 0. Okay. So R and S equal to 1 and 2, and the others are 0. Okay. Okay, so now we can write down the Hilbert space. We obtain the Hilbert space again just from what we do. So we specify a vacuum by requiring this just AR, K, annihilate the vacuum. Okay, for any K and R, okay, R equal to 1 and 2. And then the single particle state is given by just AK, R, and the dagger acting on the 0. So we denoted this as K and epsilon R. Okay. So this this describes a single photon state with polarization vector given by epsilon R. Okay, so remember epsilon R is a transverse vector. Okay, and you have two independent of them. Yes.
Should there be some normalization, like square root of 2 or like that?
Yeah, I believe so. Yeah. Let me just put the proportionality. Right. Yeah. Thank you. Okay. So so that concludes the story for quantization in the Coulomb gauge. So just to summarize, for the Coulomb gauge, so the Coulomb gauge, it's conceptually pretty simple. Okay. So the advantage of the Coulomb gauge is that we can just directly quantize physical degrees freedom. Okay. Because the unphysical degrees freedom phi just automatically equal to 0. And then the longitudinal part we can just throw away by hand, okay, using the Coulomb gauge, by promoting the Coulomb gauge condition as the operator equation. And then we can just throw it by hand. And then we just have a transverse part. And then once you have a transverse part, you can just quantize it then as free massless field. Okay? But the drawback, of course, is always not manifest Lorentz invariant. Okay? Not manifest Lorentz covariance. Okay. Any questions on this? Good. So now let's look at the Lorentz gauge. So these two are the most commonly used gauges, and also these are two representatives. Okay, two representative gauges, and they because by quantizing them, they involve in completely different procedure and the thinking. Yeah, by contrasting the thing, what's happening in the Lorentz gauge and what's happening in the Lorentz gauge actually will be very instructive. Okay, so we will just consider these two cases. So now let's move on to the Lorentz gauge. So in the Lorentz gauge, we will use a somewhat different strategy, because in the Lorentz gauge, so first is that the solving that the gauge condition become more difficult, okay, and also in the Lorentz gauge there's a residual gauge freedom, okay, so there are two things. So in the Lorentz gauge, instead we will start with this action. So we will start with this action. We will start with this this action, which we say classically can be used to fix the Lorentz gauge, okay? And when psi equal to 1, so this just become partial mu A nu and partial mu A nu, okay? So this for psi equal to 1. So you say this theory we know how to quantize. These are just 4 decoupled massively scalar fields. Okay, for psi equal to 1 is particularly simple. We just have 4 yeah. Oh, by the way, I should mention, once you have that form, and once you have this commutation relation, and once you have this relation, you can find any correlation functions of A. Okay, 2-point functions, propagator, Feynman propagator, retarded propagator, you can find all of them explicitly. So now this theory seems to be very simple. This is just like decoupled 4 matrix scalar fields. Okay, so we can just straightforwardly write down its canonical momentum. So pi nu this is just equal to A nu star, A nu dot. Okay, and the Hamiltonian density just given by 1/2 A nu dot plus, just like you have like 4 independent massive scalar fields with equation motion given by partial square A nu equal to 0. Okay? So now you can just completely take over. Okay, we can just completely take over what we did for the massive scalar. Okay, to write down the answer for the massive scalar, but we're running out of time today. So next time we will talk about. Say now you can just do treat it as a massive scalar, but then we have a problem. Okay, because we know that we just did the Coulomb gauge. We only have 2 physical degrees of freedom, but here we have 4. Okay, so somehow we have to get rid of 2. Okay, then we will find ways to get rid of the 2. Okay. Okay. Yeah. So yeah, let's stop here for today.